Swayam Prabha. Digital India. Educated India.
So welcome back. So in this lecture, I'll very briefly talk about, but maybe I'll go in detail and talk about the earthquakes which have been triggered along the Himalayan front during the historical past and recent. So as I discussed in the previous class, that we have very old earthquakes which have been triggered in Himalaya over here. Still, other than this, we have another map which shows about that the earthquakes goes back into the history. I can just try to bring that slide here and talk. So if you look at this, we have the earthquakes which have been triggered in recorded in AD 25, and then further old events, and along with that we have the recent events also which were triggered in Nepal, that is 2015 earthquake. Now what is basically happening here is that we have the frontal range of almost like more than 2,000 kilometers, and these locations which are been shown in boxes here shows the geological investigations which have been taken up to identify the signatures of the paleo earthquakes. So pretty good number of trenches were been dug across the fault scarps in Himalaya, and what we found was that there is an overlap in ages, because we try to find out the ages of the layers, different layers which are displaced layers, and try to understand that when was the event during the historic past, or maybe before that also. So these are the locations which have been listed here, the location of the trenches, and then what we observed and inferred was that there could be in two scenarios. If we consider all the trenches and the overlapping ages, then we end up saying that whole front got ruptured in two major events. One was during 1200 to 1300 AD, and another was around 1400 to 1300 AD, with a rupture of almost like 1000 kilometers or 800 kilometers. So then we have released the complete strain which was available with us. The other scenario is that even with the overlapping gauges, we can have multiple earthquakes that could have marginally ruptured the different segments. In that case, you will have an earthquake, multiple earthquake, for example in 1555, then 1505, 1255, 1344, or 1400, 1100, and so on. There is a big question that because the ages which have been found along this range in trenches during the geological investigations probably suggest that this whole area was ruptured in 1255 AD earthquake. So in that case, what we are doing, that we are saying that this may be an earthquake of magnitude greater than equal to 8.5 or less than equal to 9 or so. And in another scenario, we say that okay, all these earthquakes were of magnitude around 7.8 to 8. So these are two different things which we are talking about. Here we are talking about a very large energy released and more damage to the area, where here we are having, of course these are also damaging earthquakes, but the damage will be relatively less, okay, and the energy which has been released during this earthquake will be relatively less. So based on those earthquakes and the details, we did some exercise taking into consideration all the ages, where we can see that there are very typical events which we can put in here. Now, going back to this part, what I would like to emphasize is that if you look at the earthquakes which are triggered in 20th century, so one is this one, another is this one, and third is this one. So we have 1905, we have 1934, and we have 1950. These are the three earthquakes which we are having. Now the difference between these two earthquakes is hardly 50 years. Now after 100 years, suppose we date this events, what we are going to see is that we can say that all events occurred in a range of around 1900 plus minus 50 or so. This is just I am roughly talking about. Then in that case, I will be able to rupture this whole front, which is a bit difficult to accept. Now, if you rupture this full front, then you need a magnitude greater than or equal to 9. But this was not true, which we experience in 20th century. There were 3 earthquakes which occurred at different point of time and ruptured different portion. Similarly, based on this exercise which we did, we have tried to infer, and we are of opinion that there were 3 or more than 3 earthquakes in this region which were responsible for rupturing the complete front, and not only the 2 events which were responsible in rupturing the complete front, that were in past. Okay, like this I am talking about, that these 2 events, okay, that is 1200 AD and 1400 AD event. These were not the only 2. But if you want to infer taking into account the overlapping ages, then you can say that there were only two events. This was one and this was another one, which completely ruptured the whole front. Similarly, if you want to take this 3 earthquakes here, then also you can say that this whole front was ruptured. That is again not correct. So considering all the scenarios and the best fit scenarios, we are of opinion that Himalayan frontal thrust or the Himalayan region can host earthquakes with magnitude around 7.8 to 8.5, and but not more than that, or even less than 8.5. This is what we would like to emphasize here. This paper we have already published, which we will try to make the link available to you so that you can refer it. Now another scenario which comes up is that where these earthquakes were triggered, whether these earthquakes were triggered along the front or they were triggered in the hinterland side. So when I say that along the front or the hinterland side, then I would like to just put a sketch here that we have the Himalaya, this is like your lesser Himalaya, then you go up higher Himalayas and all that. Okay, and then in section, if you want to see, and what you are able to look at is, and that this is the section here. So we have the MCT, then we have MBT, and then we have the Himalayan frontal thrust. So MCT, MBT, and Himalayan frontal thrust. So question which is coming up is that whether this part was ruptured. I'll use different pen so that you can easily make out. So whether this portion got ruptured or this portion is getting ruptured. Okay, so out of this, like whether the earthquake was triggered here or it was along this one, this is an important part, and this what has been explained and or tried to understand through the recent earthquake of Gorkha 2015. So what it was been found that this earthquake was triggered in the down dip portion. It did not reach right up to the Himalayan front. So this is the section from this we are looking to. This is south and this is the north side. So it did not rupture the front. So if I take the section here, then you will be able to see something like this. This is the Himalayan front, and then you go up. Okay. So this goes like that. So you are having MBT somewhere here, and then you will get MCT somewhere sitting here. Okay. So this is HFT, or you can say main frontal thrust. This will be your detachment, main detachment, or the main Himalayan thrust. Okay, this is also a detachment or décollement. This is your MBT. So the question now is that, and what has happened, what was experienced was that this did not come right up to the surface. It ruptured somewhere over here actually. So still this portion is likely to rupture, and this is what people are inferring, or the research groups are inferring, that this will rupture in near future. So this part which got ruptured was very much similar to the earthquake which was triggered in 1833, and then what we had was in 2015. This portion was ruptured, and they believe that this was ruptured in 1934. This is in Bihar, Nepal earthquake. So if this cycle what we see is correct, that 1833 was in hinterland side and 1934 was along the front, then hinterland side we had another one 2015. So next we can expect in the frontal part. So this is what we have, like many groups are talking about, that we can expect the another event, the major one similar to 1934 along the Himalayan front in near future. So these are the scenarios which are been given, like that the rupture initiates far behind the Himalayan front along MHT, and then the deformation propagates towards the south. Now I'll just quickly show you some results which we have done and what type of studies we are doing to understand the past earthquakes and what are the signatures we see on the surface. This is from Himalaya, the case study, as well as I'll talk about some very important modification of landscape, or the sculpturing of landscape took place from Great Run of Kutch, Western India. So this area falls close to Chandigarh, where we have a very prominent Himalayan frontal thrust fault line, and then along with that we have another imbricated fault system which have been seen between MBT and HFT. MBT is your main boundary thrust. So this area is we say Chandigarh and Pinjore Doon. There is in this area which has been shown here is the intermountain valley between the two hill ranges. This is Shivaliks and this is the Lesser Himalayas which we see. So there is a valley between that. So the study which we conducted in this area is from this region. So we have marked based on our interpretations on satellite data several fault lines. Chandigarh is sitting somewhere over here, that is in your Indo-Gangetic plain, and then the frontal part starts from this place. So we have a number of faults. This is the part of the HFT named as Chandigarh fault, and just move ahead towards the northwest northeast, you will find there is another fault which is running and crossing the Doon Valley, Pinjore Doon Valley, and we have named this as an Pinjore Garden fault. Then there is an oblique fault here, Jajra fault. We have another one which is Barsar thrust, and then we are having another fault named as Taksal fault. Now this Taksal fault is your right lateral strike slip. So based on the topography of the active faults, we classify these active faults in different types. For example, whether they are thrust faults, or they are normal faults, or they are strike slip faults. So mostly the faults which you see here, this Himalayan frontal thrust is in thrust type, so it's very typical in the compressional tectonic environment. This is also thrust, but this one is plied oblique, which shows both component thrust and reverse thrust and strike slip component. This is pure thrust, and this is we are having right lateral strike slip. So we have very beautiful offset of streams and offset of landforms which were been identified, and based on this the mechanism of the faulting, that is which type of faulting it is, we have decided. Now my only point here which is like very important one, that if you take the scale, this is hardly 30 to 40 kilometers, or maybe less than that, and within that distance we are having almost 1, 2, 3, 4 and 5 faults which are sitting, and all 5s are active fault. So the hazard posed by these faults, because these faults are capable of triggering large magnitude earthquake, that's what our research says. So any earthquake hosted by these faults, if magnitude is greater than 7, definitely the region which are sitting in the Indo-Gangetic plain, in the nearby area or in the vicinity of these faults, are definitely going to be affected. So from hazard point of view, that is seismic hazard assessment, need to consider these faults and what is the history of earthquakes on this fault. That is also another important point which we need to consider. Now in one of my class I was talking about the most important part which we should deal with will be one is the magnitude of the earthquake, then second is that what will be the expected peak ground acceleration at the site of interest. So this is very important, because it will vary from place to place, that is ground acceleration will not be the same at all locations, because it depends highly on the site conditions. So these are very important points which we will discuss when we are talking about the ground deformation or ground effect, a different topic, but it is related to the seismic hazard. So after identification, what we do, I will just quickly browse through a couple of slides. We take the we undertake detailed mapping of the landforms which we have identified from the satellite data. So this is the high resolution satellite image, cartosat image, and the resolution is almost at about 2 to 2.5 meters. And what we do is that we use this image, which is ortho corrected, and this image as an stereo vision and with the stereo vision capability, so that we see the terrain in 3 dimension. That helps us in identifying the deformation which is preserved on the surface, and young landforms are been displaced. Now, for example, we have put the arrows here. You will not be able to differentiate easily whether this side is gone up or this side is down. But since we have looked this image in 3 dimension or 3D perspective view, we know that this side is up, this is down, and relatively to this fault line, this side is up and this is down. So we know this very clearly, and we understand that what are the sharp features which we have picked up. So the portion, the photograph which has been shown here is taken from this place here, and this scarp, which we say fault scarp, this fault scarp is along the Pinjore Garden fault. So what we do after the detailed mapping, we take an profile, topographic profile. Either you can use very high resolution like GPS RTK, you can do real time kinematic, or you can take with the total station also. This information is available because when we have the edges of this surface, then we can easily talk about that how much what was the rate of uplift of this surface in time. Okay. So then that that can help us in understanding that what is the frequency of earthquakes which have been hosted on this particular fault in past. Even we can talk about to some extent the future prediction. So this is one of the trench which we have dug over here on the Jajra fault, and this showed us a very clear cut branching pattern, and what we typically say as an positive flower structure. This positive flower structure is commonly seen in strike slip faults. The positive flower structure means we are having these are all popped up. Okay, so this has gone up, this has gone up like that. So this is a very typical positive flower structure with developed because of the right lateral movement and also the reverse component which has been seen. Now what we do is a very simple way we try to identify or judge the events. So we see the cross-cutting relationship of the faults, and where the fault or the deformation is getting terminated, that will be our capping unit. So for example, if you have to date this event, that is the faulting which displays this gravel but was finally capped. So there was no deformation on top of this, so this layer was not disturbed. So at least you can say that, okay, if you are having the age, these are the ages. Carbon 14 as well as OSL ages, optically stimulated illumination. We collect quartz samples or the sand samples which are not exposed to the sunlight, then we process that completely in our lab. So based on the energy or the dose which got accumulated over the time in the buried quartz, that is exposed and stimulated artificially or with the help of what we say optically stimulated illuminations, and then the energy released is measured, and then we do that. Okay, so that is a completely different topic. I am not going to talk about that here, but the important point is that these are the ages which we are getting from OSL. For example, are the depositional age, that is the time at which the sand grain or the sand or the sediments got deposited and buried. So these are the ages which we are having from OSL, the ages with the C number here, which we are letter, are all charcoal ages. So we do AMS, accelerator mass spectrometry, dating that sample ages we are having. Now what we see is that since this is the capping unit, then we try to look at the oldest age of this unit, which is close to, for example, the contact between the unit B and then unit E. So if we get that we will pick up. So for example, if we take this one age of the capping unit, which is the probably the oldest one over here, and then minimum age of this one somewhere here. Okay, so we got what we got was the age here, that is of this unit, which was because this unit was also disturbed, but it was not the fault did not rupture or fracture this unit, that is unit E. So we took the age of this unit D. So hence we can bracket the event that we can say that this earthquake which ruptured or deformed the sediments occurred somewhere between AD 1223 and AD 1375, or we can say 1442. So this will be the age bracket. We can say that this becomes an event of like AD 1200 to 1300 AD event. So these are the ways which we try to incorporate in our data, and then the features which were been shown in the previous slide, we try to map the displacements in the exposed trenches as shown by the arrows. This is what we call the shear fabric. So we are having most of the gravels which are elongated over here along the fault. So fault runs somewhere over here like this, and then like this also. Okay. So basically what we do is that this is another that's the same figure but the different location which we dug the trench across this. So we open up the another trench here to look at the different deformation pattern as well as the events which have occurred. As I explained in the previous trench, the sections which we excavated across the fault scarp, that was from Jajra fault. This is from across the Pinjore Garden fault. So we identified, like we say that okay fine, because this is the topmost unit or the unit which on there is no capping here because we were unable to find the capping on this, and the most recent event took place along this fault where the younger unit that was also displaced. So we bracketed the event because there was some problems related to the top unit, but anyways, in short, what we are interested here to identify the deformation pattern and try to bracket the events. So this is again similar shear fabric which has been shown here, and you have the deformation pattern which has been like in folding. We see here like this is the fault plane, and the folding is taking place over like that. Okay. Now this is the model which we have proposed, but of course the most important part why I am showing this model is that these are all out of sequence events, okay, which we have identified on Pinjore Garden and Jajra fault. They are all out of sequence. So the sequential pattern which has been suggested is that from the hinterland side you will have the deformation here, then this will propagate over here, and then in the frontal part. So this is like for example what we say the HFT, then this is your another we can say Pinjore Garden fault, and then one is your another one which is coming here is Jajra fault, and then we are having let's say MBT. So if we say sequence faulting and sequence deformation, then what we should have got is that first earthquake would have occurred here, then it was next to here, and third here. But this was not true in the case what we identified, on this faults, probably this were the events which we talk about, the out of sequence. But one very surprising thing which we noticed was, so this was where our understanding that what we see here, but the dates or the ages which we got, what we found was that all this fault, the ages of the events which we bracketed are falling in the same domain of the time range. So HFT we did not do, but previous we have done one trench on that, and that suggests about 1300 to 1400 AD event. Here also it was more or less similar, it was more or less similar. So there was a big confusion which was created, that all these faults probably moved together in one go, or there were different events in the same the time range, or either we say 100 years time range or 150 years time range. So that is another scenario which we have suggested. But this the topography which we have picked up on from the Pinjore Garden fault clearly suggests that there is an oblique slip partitioning which is taking place, and the case of an slip partitioning over here. So these are the scenarios which we have suggested, that is quite possible that in scenario 1 what we suggest is that there wasn't deformation or the earthquake which occurred close to the brittle ductile boundary along the ramp and ruptured right up to the surface, even displaced. The displacement was been consumed by the Pinjore Garden and Jajra fault. In second scenario, what we suggest is that there was another event, because if you trigger an event here and bring the rupture on close to the frontal part, then you need a very large magnitude earthquake. But here if it is on the ramp side, then taken up by the flat structure, then probably these two fault move together in one earthquake. Or there is a scenario that there was a major earthquake which separately moved this HFT. Okay. So these are the three scenarios which we have projected, that either all the rupture, the complete locked segment, that is because this is a locked segment what we are looking at, it ruptured right up to the surface, breaking all the faults. Then independent seismic events which ruptured the updip portion of the MHD. This is the updip portion of the MHD, similar to Gorkha earthquake. And another scenario was the seismic event which took place after the event which occurred here on Pinjore Garden and Jajra fault, resulted into the rupture here. And this is the scenario which we were talking in the previous slide, similar like 1934, and this was similar like 2015, and then before that there was 1803. Okay. So these two have already done with, so this has occurred, so another could be expected here. So I'll stop here, and I will continue in the next lecture with more examples from Kutch.